is Harvey Fiala. He's gotten to be one of my favorite presenters here. He's been around long enough to have seen and done a lot of things, and he said that if I read his full biography, it's not going to leave enough room for the talk. He got started working with this kind of technology, and I'm sorry, the font is just impossible to read at a distance here. He grew up on a farm in North Dakota, and he started doing gravity research with precessing gyros and out-of-balance wheels in his father's basement at the age of 8. And he went on to go to college at St. John's University in Minnesota, and he got his bachelor's degree in electrical engineering from North Dakota State University in 1958. He's been an instructor. He's been a student of Richard P. Feynman, and he's also worked with a number of different companies, including Bendix and General Electric and Hughes Aircraft. And so let's please give a warm welcome to our very experienced and very knowledgeable presenter, Harvey Fiala.
Thank you, Mike. Well, after listening to some of the presenters, in particular, like the first presentation by Ralph Ring, and then by last night's last one by David Yerth, and even by Mike Wendell just now. What they've done makes me feel so insignificant that I wonder about things. But you see, the first presenter, Ralph Ring, he showed a spaceship or a saucer that was 6 inches in water, and if you put 100,000 pounds on it, it didn't sink anymore, and it would fly and so forth. And if that stuff is real, that is, my stuff is so insignificant that, but I haven't seen that demonstration yet, but it's credible. And last night, David Yerth spoke about, I'll call it the new physics, and where Einstein did a lot of good work, but if you follow just what he did and don't deviate from it, you're going to go down the wrong path all your life, and that's what we've been doing for so long that it's pitiful. And Mike Wendell here, if you have a phase difference between two beams, it can cause a crystal to not know what it should do, and it can change it, and in probably unpredictable ways, which would probably make it hard to replicate. But anyhow, I've got to find my main sheet of paper here. Did I leave that back here by any chance? No, there's just two of them. No, that's... If you'll excuse me, I'm looking for, I have one sheet which guides my whole presentation, and it seems to be the one that I cannot find right now. Uh, no, it isn't. Thank you. That is really strange. Thank you. I have another copy without all my notes on it, but okay, I'll just mention that he mentioned I got interested in this at the age of 8, and I used to play with gyroscopes, and I'd build little wheels like a bicycle wheel, only, you know, if you have spokes, you tilt them down a little teeny bit, then a weight should roll downhill, and if these are tilted up a little bit, that should roll toward the center, and it should go out of balance and start spinning, and, you know, at that age. And then when I had my first class in calculus, I proved that can't work. You know, it's an interesting combination, but I proved it can't work. And the only background I have, my father and grandfather weren't Nikola Tesla or PhDs and so forth. But my father used to take 30 horsepower motors, rewire them and make welders out of them and build welders to help support the family. And he made a windmill and set up a 40 volt electrical system, so our farm had the first electricity in the neighborhood. And I used to rewind electric motors for washing machines when I was a kid, just as a kind of a background. And for the last 3 years, I've had 3 generations of my family here. My wife is here today, and my son John and his wife Patty and their son John Arthur, who are playing a role here. And my son Jim, he had to leave during the night. He had his whole family here. And at the INE conference, Institute for New Energy, I've had 3 generations there for 3 years also. And so it's important to me, it's an honor and a privilege to be able to talk to a group like this. And you know, as my wife boarded the airplane on the way here, an interesting happened. After we were seated, a beautiful blonde came on and sat down in the coach section. And then there was one seat open up in first class. And she saw this and she walked up and she sat down, and the stewardess came up to her and says, "Ma'am, may I see your seat ticket, please?" And she showed it to her and says, you belong back in 27A, and this is first class here. And she says, "I'm a blonde and I'm beautiful and I'm intelligent and I'm going to Salt Lake City and I'm going to go first class and no one's going to stop me." And she says, "Please, ma'am, just go back without any scene." And the lady says, "Nope, I'm a blonde, I'm beautiful, I'm intelligent, and I'm going to Salt Lake City and I'm going to go first class and no one's going to stop me." So she kind of gave up and she asked a male steward to, so he went through the same routine and she wouldn't budge. So the stewardess went to the pilot, mentioned this to the pilot, and and the pilot says, "Okay, I'll go take care of it." And the co-pilot says, "Wait a minute now." He says, let me handle it. I'm married to a blonde and I know how they think and I speak their language." So the co-pilot went up to her and says, "Ma'am, may I see your ticket?" And he says, "You really belong back in 27A. And she says, "Nope, I'm a blonde, I'm beautiful, and I'm intelligent, and I'm going to Salt Lake City, and I'm going to go first class, and no one's going to stop me." And so the co-pilot went and whispered into her ear something. And she sat back and said, "Oh, I'm sorry, I didn't realize this." And she got up and went straight back to 27A. And everyone was amazed, and the pilot asked the co-pilot, "Well, what on earth did you say to her?" He whispered into her, he says, "Ma'am, first class isn't going to Salt Lake City." I'm going to mention a few things before I get to my talk proper that prepared me for this. My first physics class, the chairman of the physics department was teaching it. After class, I walked up to him and I says, "May I ask you a question?" He said, "Sure." So I said, "Suppose you go way out in deep space where there's nothing and you put a ping pong ball out there. And then 186,000 miles away, which is how far light's supposed to travel in 1 second, suppose you create a new planet at t equals 0. Then I asked him, how long will it take for the gravitational field from that newly created planet to travel out and grab a hold of that ping pong ball and start pulling it toward it?" And you know what his answer was? He looked at me and says, "Are you crazy?" That was his answer. Now that could cause someone to give up on it, you know, think, man, I'm a kook or something. But okay, 3 years later, I wrote an article called Gravity, a New Form of Communication, ? Because at that point I thought, you know, if gravity is instantaneous, it would certainly be a good thing to develop. And it's a little harder to work with than electrons and magnetic and electric fields. But I read that Dr. Fritz Zwicky from Caltech, due to astronomical observations, he thought it was at twice the speed of light. Well, that sounds kind of weird. And all the learned scientists interpret the speed of gravity to be at the speed of light. It's kind of a consequence of relativity. Of course, we know that a lot of good work was done in relativity, but it wasn't done and it wasn't all correct, and so it led us down the wrong path for many, many years, and we're still on the wrong path, basically. And so when I got to Caltech, I studied that problem further. I wrote up 3 different proposals on how to measure the speed of gravitational interaction, and my wife actually suggested one of them, which is very interesting. And I worked with Dr. Feynman on it, and actually Hughes Aircraft, where I first worked, they sponsored me on a gravity research program besides working on the missiles, a part-time thing. And I spent about a year on it. And then with Dr. Feynman, he proved to me with some equations that the effect you're looking for cannot be measured because 2 components cancel each other. And so I stopped the research at Hughes at that time just because I didn't want to spend the money on it. And and I continued my interest. And meanwhile, back in college, though, I developed what I called, on paper, a gravitational function generator. You know, with a regular function generator, you can put out sine waves, square waves, pulse waves, negative pulses, sawtooth waves, and triangular waves, anything. And I designed one that put out gravitational waveforms, really, and it worked in the near zone field. It's nothing but put that first slide on, John, please. Just the first picture back here. Yeah, if you could turn that on. I meant to have a lot more slides with me, and at the last minute, they weren't on my laptop. So, but there's a sketch. If you take a disc and you drill 2 holes in it, and you put I'll say a tuning fork tuned to the proper frequency for the spin rate of that disc, as that hole passes nearby, there'll be less gravitational attraction on it. And when the hole passes 9 degrees to it, the gravitational field will be maximum. So it kind of puts out a negative pulse shape. And actually, by Fourier analysis, you can place different size holes at different angles, and you can create a perfectly negative pulse. And similarly, if you put a double density thing in the slots, you'll have a positive pulse. And you can, again, make a positive pulse of any wave shape. And I published this. In fact, I had a paper to the Gravity Research Foundation. And then after that was published, I started getting calls from, believe it or not, the Army and the Navy and the Air Force. And I saved all those letters. They're still in my files. They heard that I was interested in gravity research and that I might have something interesting, and they all wanted me to disclose, you know, everything I had to them. So I responded to them, but it's something so simple that this works in the near zone field, not in the radiated field. And the near zone field is conservative, and it's not radiated, but that's such a simple thing that it really, it depends on how you look at things. That wasn't any humongous breakthrough, it's just an application of Fourier analysis. And put the second one on while we're here. Later, that upper thing there is basically the heart of my talk. It's an inertial propulsion device with only one moving part. Now I hand sketched this, and it's very hard to draw perspective or an isometric on stuff with fancy curves. And so later on, I redid that. You can take that off now, it's terrible looking. I redid it with SolidWorks, which is like AutoCAD. And I haven't fully learned SolidWorks yet, but is there anyone in this audience who has worked with SolidWorks and knows how to do it? Pardon? Okay, after this talk is over, I'd like you to give me your name because I have some questions. I'd like to be able to communicate with you and ask you a question because SolidWorks is supposed to be the most user-friendly, most powerful program. I've had AutoCAD for 15 or 20 years, and it was only two-dimensional. I didn't upgrade to the 3D stuff, and so I've got half of my drawings done with SolidWorks, and the other half I didn't quite finish yet. And at this point, I'm going to define inertial propulsion, so you can put up the first, I guess I have control of it here. This is an abstract. Basically, inertial propulsion may be defined as propelling a vehicle without any propellant of any kind and without the use of an external field, like if you apply a magnetic or electric field to something to move it, that doesn't count. That's not inertial propulsion. And I'll be presenting three separate processes that do not require a propellant, and they do not produce an equal and opposite reaction against any external form of matter in our local reference frame. And they do not violate Newton's laws in what I'll call the universal reference frame. I'll explain that in a little more depth, a little bit more. They do not violate the law of conservation of angular momentum. Actually, it looks like it does, but the gravitational field from the Earth plays a big role in everything here. And when you consider the Earth, the law of angular momentum is not violated in that system. On a local basis, it looks like, hey, this can't work, but that is not the case. And now your weight is a function of your mass and the strength of gravity. That's how much you weigh. And there's various theories that talk about, now your inertia, if you're moving, is a function of your mass. And there's theories that reduce the amount of inertia that a mass can have. And I'll be talking about one of those methods. And I would like to mention one thing. Suppose I have a boat here. Maybe it's 20 feet long, and maybe it weighs 150 pounds, and maybe I weigh 150 pounds. Now, if I start walking forward with some good thrust, I'm going to move forward, and you know what's going to happen to the boat? It's going to move backward a little in the water. And if I back up, the boat's going to move forward again, and I'm going to move back. But suppose I do this. Suppose I walk forward, and the boat moves back a little, and I move forward. Now, suppose I had a magic switch, and I turn my mass to zero, so I have no inertia. Now I can move back to the back of the boat, and the boat won't have any reaction. And so the boat will stay forward, and I move to the back end. Now I'm going to take the switch, and I'm going to turn my weight full on, my mass full on. And I'm going to walk forward again, and I'm going to turn it off, and I'm going to back up, and I'm going to keep this. This is a cycle. Now if I do that, the boat will keep moving. Actually, it'll stop, then it'll move, then it'll stop, and then it'll move. And of course, we don't have a switch to turn our mass or our inertia off, but there is a process with dealing with precession that reduces the inertia. And I'll mention that according to everything I've studied, Alex Jones, who died a few years ago, I'll call him the father of inertial propulsion, because Dr. Eric Lathwaite, he's the one that developed the monorail, the magnetic levitation. He was a true genius. And one day he got a phone call, and Alex Jones responded to the phone call. You've probably seen this. There's a British broadcasting company video called The Heretic, and Alex Jones came in, put a device on the table, and plugged it in, got a motor going on it, and he lifted up a thing and let it go, and the table lurched forward 2 or 3 feet. And to repeat it, he'd have to recycle it. But that was the first genuine application of inertial propulsion. So I'm going to call him the father of inertial propulsion. And Eric Lathwaite kind of stole those ideas in the sense that he never gave credit back to Alex Jones, except BBC published this thing documenting the fact that Alex Jones gave to him. I've corresponded with Alex's children. They kind of think poorly of Eric Lathwaite because he stole his ideas. But he went on he's the one that took a 40-pound rotor at the end of a 3 or 4 foot rod, and it lifted up and put it overhead. Now, normally, it takes a strong man to lift 40 pounds, and there's no way you can do it with one, and he did it with one finger. But he precessed it by if you pick it up with your left hand and then hold it with your finger and start moving and torquing it, its weight literally disappears. Actually, if I weigh 150 and it weighed 40, a scale would show 190 weight. And that weight doesn't disappear from the scale, but I can lift it way overhead, and once I stop torquing it, the weight will reappear, and I won't be able to hold it there, so I'm forced to keep torquing it slowly and lower it back down. And the Royal Society that he was presenting this, they thought he was espousing violating Newton's laws, and so he was literally blackballed, which was really sad and a terrible mistake on the part of those that did that to him. And Harold Aspden is a brilliant man. In fact, I just got a one-page email from him about 3 or 4 days ago. I've corresponded with him. He picked up on the Jones-Lathwaite type phenomena, and he presented a configuration that I'll show later on. And there's people like Scott Strahan, who built a device based on, I'll call it Lathwaite's type or Aspden's type configuration, and it is supposed to lose all its weight and even lift 7 times its own weight and things like that. And later reports showed that when it was tested by scientists, that there was no loss of weight at all. And Tom Vallone, who used to come to these meetings here, he has the Integrity Research Institute in Washington, D.C. He attended a special conference in Canada a couple of years ago, and he videotaped a demonstration by Scott Strahan, which it appeared to lift up a little bit. But I call that, it has to stay up. I call that a transient phenomena, because the fact that I can take a 50-pound weight and get it overhead, that's if it's spinning fast and put torque on it, then it precesses. We had our youngest daughter, a young girl at that time. That was in 1996. The fact that you can do that temporarily, I call that a transient response. If his device stayed up or showed a continued loss of weight, like even only 10% loss of its weight is continuous, then that is very important. And so, I've searched worldwide for any sign of something that would lose weight continuously or be able to levitate. And you hear reports of 100 different devices that do that, but words are cheap. And so, and I've never heard a single one that's been verified. So to my experience, there's nothing that can levitate, let alone go straight up. And you've heard of John R. Searle's device, which take off, and even the Hamill device, which is way too suspicious. But the John R. Searle device was documented once a month by the British Broadcasting Company, and it had this plasma glow around it, which reduces the pressure inside, makes it a vacuum, and the temperature drops. And if there's a vacuum, if you have a big balloon, it's going to go straight up like the dirigible, see? And so that accounts for that kind of levitation in my understanding of it. And so far I've not come across. Now there's two types of inertial propulsion. The type that Alex Jones first demonstrated, it'll move it horizontally, and it'll move and stop, or if you rig it up device with multiple cylinder, I'll call it, it'll keep moving. But it cannot keep accelerating. If something could continue to accelerate, then that could be used to go to the planets or to the stars. And if something could accelerate, for example, at 2 Gs, it would take 2 years to get to Alpha Centauri. You'd have to speed up to approximately twice the speed of light. Then you'd have to slow yourself down, go in orbit around Alpha Centauri for a year to make observations, and then speed back, turn yourself around, come back to the Earth, and you'd be back here 5 years later, and your wife and your children are still here. A few of them would have graduated and so forth, but they wouldn't be long dead like Einstein's theory predicts. And in 1999, NASA started a program called the BPP, the Breakthrough Propulsion Physics Program, which was a very good program. And they got like one a day inputs from, not from me, but from people who thought they had something. And really, out of every 100 things, the people they really believe in what they're talking about. And 1% of them is total fraud. They can defraud people and try to raise money and so forth. But the British, the BPP program, they stopped it after 3 or 4 years just due to lack of funds. And they classified all these different devices that can move into oscillation thrusters, which work off of something called stiction. That's one term for it. And also gyroscopic devices and electrogravitic devices. Electrogravitic is like what Townsend T. Brown came up with. He found that if you have a capacitor and if you charge it, now as I understood it back in 1956, when the first reports on it from the British Journal of the British Interplanetary Society came out, they had a tutorial on it, and it said that as you're charging a capacitor, there's a gravity vector perpendicular to the direction of the charge. And once you stop charging it, that vector disappears. And if you discharge it, the vector turns into the reverse direction until it's discharged. And that's called, there's usually a voltage of 40,000 volts or more, even up to 200,000 volts. And when you get something like that, there's an ion wind. It ionizes the air, and there's a big downflow, which provides some lift to it. And so most of the electrogravitic type of thrust, which levitates, but they attribute it to ion wind. If you put it in a vacuum, it doesn't really lift any longer. And there's some reports, they supposedly unclassified them. In 1956, after I was communicating with the British Interplanetary Society, I didn't have Townsend Brown's address. They classified it top secret, so I couldn't get any more information on it. And supposedly those reports have all been declassified. And if there was something to, if they measured, okay, 98% of it is ion wind, but maybe 2% is a true electrogravitic effect. I do not believe that the government would have declassified that part, and so I do not know the answer to that. It is possible that there is some electrogravitic effect, and there's a lot of reports that the B-2 bomber, the stealth bomber, incorporates some of that technology. Now, there's back in 1960, there was an article on the Dean drive. Norman Dean built a drive which was supposed to develop a thrust. It was just it had oscillating masses which do something like this, and basically with stiction, you know, if you move quickly in one direction, you'll overcome the static friction. Then if you move back slowly, whatever you're on won't move because you're not overcoming the static friction. Then if you move quickly again, and so that's the thing, if you have an eccentric mass, it'll slowly move like this. And I spoke to Dr. Feynman about that, and he says the best way to analyze whether there's something real there, if you had the liberty of photographing it, during one cycle photograph it every 30 or 40 degrees, and study, assign a mass to each of the parts, and figure out where the center of mass is. And as the cycle progresses, you know, if the center of mass move forward a little bit and back only a little bit and forward a little bit and back only a little bit, that's fine. But the center of mass in the Dean device never moved. And I proved that mathematically in 1960. And there's been, of course, the fact that it's the NASA with the BPP recognized that right off. And there are many, many reports on it. I have a lot of respect for people who publish these reports because they're getting information out to people so that people don't try to reinvent the wheel. And also, it'd be a better service if they say, hey, by the way, this thing doesn't really work. But if you're some kind of genius, you might figure out how to make it work, see? So it's good to disseminate that information without saying, hey, here's a great idea. We know that it doesn't work, though. But so I have a lot of respect for. Now, the Integrity Research Institute publishes almost anything and everything that has some credibility to it. And the Thornton drive, it's in the water in a swimming pool, and some people get in the boat and it moves them across. And it'll actually get up to a certain speed. And I used differential equations this is about 15 years ago or so. I used differential equations to show that, and I call it's like the stiction principle, only there's no friction. It's resistance to the medium. If you're driving a car 25 miles an hour, there's a little bit of wind resistance, not much. But if you're going 100 miles an hour, there's a heck of a lot of wind resistance, and 85% of your gasoline is being used just to buck the wind. And I call that the nonlinear response to a viscous medium, whether it's air or water or whatever. And in the case of the Thornton device, if you have a front of a boat which penetrates the water nicely, and the back of a boat, in his thing he had a device which moved backward quickly, and so the boat thrust forward. If you have a big, broad back, it won't make much progress in the water. And then it moved forward slowly, and so the boat didn't move backward much at all. And then it moved backward again, the boat lurched forward. So it'll get up to a speed like 5 miles an hour or something like that, but it can never continue to accelerate. And I communicated this to Mr. Thornton, and with differential equations I could redesign his boat front and his boat rear so that it would increase his thrust by 15%. But he wasn't interested in that because I was claiming that it was not inertial propulsion. And at Caltech, I used to get calls like there's a guy named Laszlo Matyas. In fact, he lived only 15 or 20 miles from me. they asked me to go out there and check out his device in his garage. He had an anti-gravity machine. Of course it couldn't work. And another guy had a bigger contraption near Mount Palomar, the 200-inch telescope out in the mountains. Of course, it didn't work either. And there's a pendulum test to test whether something is really good. And it was mentioned in the BPP report. Now, the real pendulum test would have a flat platform with 4 strings suspending it. And if you put a device on it, if it stays moved off of center, then you've got sustained acceleration, which is important. If it moves forward and then back again and oscillates about the center, then it's no good. But it could have just motion like the thing I'm talking about, I'm calling MMT, motion by mass displacement. And it does not produce sustained acceleration, so I'm not making that claim. But I am claiming that this is just a first step toward, before you walk, you got to crawl. Before you run, you got to walk. Before you fly, you got to run. And this is a first step, which I believe is so solid that it's the first time that it's practical to make a device like that. And now we can start with, this is Dr. Eric Lathwaite in his later years. And here you can see he was tricky enough to take a flywheel and break it up into little metals so that instead of being one solid rim, you can examine the forces on it as you torque it and it twists sideways. You can study the forces that are actually involved by taking a video of that bicycle wheel. That's pretty neat trick there. And here, this is something that the BPP report showed. And although it's good, they had a lot of fallacies in it. They called the gyroscopic anti-gravity, I'll say by Lathwaite or by Scott Stracan, they called an oscillation thruster, and that's wrong. Wrong classification for it. Yeah. Testing, okay. This describes the Lathwaite experiment, and as I said, I built the device, and every member of our family, our young daughter raised actually it was a 29-pound flywheel from an old vehicle. And they went on to describe the phenomenon a little bit more. This is, when you turn that main spindle, that's torquing it. If it's precessing naturally, and the term natural precession applies to gravity is pulling down on those, and so they'll go around in a horizontal circle. That's called natural precession. That term is not universally known, but it's a term that I use, and a lot of people do use it. And if you torque it like this, they'll raise up. That's called a forcing torque. If you actually applied some friction to it to slow it down, that's called a slowing torque, and they would drop down slowly. And this was their conclusion. You should never use the term push, for example, when you're talking about propulsion, because that's an undefined term. And whenever I discuss something, I'll define the terms exactly as I'm using them. Someone else may use the same term, and they may have a different meaning to it. But push could imply acceleration or just plain old motion. This talks about the electrogravitic thing, which I just covered. And that's Townsend T. Brown the inventor of the discoverer of the electrogravitic effect, if in fact there is such an effect. It'd be wonderful if there is. This is the guy from Canada. Pardon? Yeah, David Hamill. And this here is, this is an important picture here. This is John R. Searle. And if this was taken back in the 70s, early 70s, and if that's real, that is very significant. And I'm trying to contact the British Broadcasting Company. I just haven't had the time. They supposedly took movies of his flying devices. And if you had a movie of a single movie of a flying device, that is very, very important, because it would show that this Searle effect, whatever it is real. And it might include what you would call an anti-gravity component, which could buck the force of gravity. And in those days, well, I mean, you can fake a still picture nowadays, and nowadays you can fake a movie. You can do anything, Star Trek. But in those days you couldn't. And so a movie from those days, if it really was an old one, it would be significant. And I think there's a reasonable chance that the John R. Searle effect could be used to oppose gravity. And on the other hand, if there's a 30-foot diameter plasma sphere around that device, and it's got a vacuum inside, that could be what is sustaining it. It's like floating in a pool. There's a book that's probably available on the shelf out here. I'd recommend everyone buy that book and read it. And here's, I think his name is Robert Cook. I corresponded with him like 10 years ago, and he's upgraded his system. This is an animated thing, and it's supposed to produce thrust by having unbalanced centrifugal force. Well, I graphically, I advanced that to one full cycle about every 30 degrees, and I showed that the center of mass does not move, and it cannot move. When something moves, if a mass moves, there's a reaction. Part of the frame moves backward. If you move a heavy mass forward, the frame moves backward a little. If there's a centrifugal force, the device is pulling out on it, and it's going to pull this way. But the forces all do not allow the center mass to move at all. Although that's a very impressive thing. You could look up the Cook device on the internet. And here's just a very simple thing. It's called a gyroscope. I don't use the term gyroscope. That's a simple rotor. And gravity is pulling down on it. It has a weight of W, call it 7 pounds. And it'll go round and round. That's very simple. Now I'm going to distinguish between the term gyroscope and a flywheel or a rotor. In the old days, well, first off, a gyroscope was something far more complex. It'd have at least one rotor, and it'd have a gimbal system, and it could be gimbaled about all 3 axes, and that would be called a gyroscope. The term scope itself implies something, none of which exists in this drawing here. And right now, gyroscopes, they have fiber optic gyroscopes. No moving parts whatsoever. A beam of light travels in a fiber optic circle. And they have fiber optic, and there's laser gyroscopes. Where the beam of light, there's 4 mirrors, and if you rotate it one way or the other, the 2 contra-rotating beams go in and out of phase, and you measure the amount of rotation. But see, there's no moving parts. And some of these gyroscopes are the size of a dime. So I don't like the word gyroscope anymore to be applied to inertial propulsion, but the name sticks. Here it just shows, notice if that moves 180 degrees from there to there, you've just had a mass, in this case 6.31 pounds. If that moves all the way around here, 6 pounds of mass moved a total of 24 inches. And if you stop it there, you've accomplished something. If you let it go, it gets back to where it started, and you haven't accomplished anything. So being an electrical engineer, you know, a sine wave goes up and it goes down and up and down. And if you rectify the bottom half and flip it up, you've accomplished something. And here, it simply amounts to, if it goes this way and then that way, rectify the bottom half if you can. And 10 years ago or more, in 1996, John and I, we built a device that pedestal right there, or pivot point, we put there. See, this is what I call the axle or the lever arm. It had a lever arm out there also. And when it comes around here, the other side of the lever arm is out here. And if it comes onto a new pivot point, and if you jerk this pivot point away, it goes like this, then it'll go like this, then like that, then like that. And the point is, it moves 24 inches every half cycle. And if you can implement that, okay, you've got a simple inertial propulsion, but that's not practical to implement. It can be done, but the mechanizing that very tricky little pivot point on a stationary platform, it's pretty tricky, and it doesn't accomplish that much, so it's not worth doing. But it illustrates that you can move mass without a force being involved. That's the main conclusion there. This is just a picture of a simple device that leads up to the device that I'm going to show. Here's an example of a device that John built for me. We used it to run tests with. The tests, we were trying to test for sustained acceleration, and the tests, because this device was actually quite crude, it's precise, but in building it we had to reduce the friction. We opened up some holes, and it was kind of sloppy, so our test results were inconclusive in trying to demonstrate sustained acceleration. And now here, okay, by golly, I master SolidWorks a little teeny bit. This is one of the embodiments of the inertial propulsion that I'm one of 4 different configurations. There's the rotor. I won't call it a gyroscope. And there's a bearing there. And here's a motor. And there's a gimbal system and a little platform with wheels on it. And now, gravity operates this device. And gravity pulls down on it, so that wheel is going to want to precess round and round like that. Now you have to pay attention very closely here. As it's going around, suddenly it's being supported. Now once you support something, it stops precessing. So the wheel would stop, except for the fact, now this wheel, in precessing this way, the wheel is going round and round like that. And this wheel over here is going round and round like this. Now when this here is called a support ring, and it raises up an inch or so, and it's riding on this bearing. And that bearing lifts it up a teeny bit, and it causes this to press down a teeny bit and to crawl onto this, I call the V-groove track. It's like a V-belt, like on your automobile engine. And now, being the fact that this axle or lever arm is spinning round and round, it's going to rotate the system round until this V-groove collar drops off the end of that track over there. When it drops off the end of the track, gravity will be pulling on it. It's going to precess, and it's going to precess. At that point, this disc will be over here, and it's going to precess Now notice that the disc is between the support ring and the V-groove track. And so it's going to be over here between, and it's going to precess around, and then it's going to stop precessing and be what I'll call, this is going to scoot it over or retrace it. And when it's retracing it, that's when you get a motion. When this is grabbing here and it's moving a big mass this way, and when it moves a big mass this way, we'll pretend it moved only straight. Then the platform is the reaction is going to move the platform forward. So that disc, if the disc weighed 100 pounds and all this other stuff weighed only 1 pound, when that disc moves over here, the platform would move 99% of the way across there. If the machinery weighed exactly as much as the rotor, then when the rotor moves over here, we'll say it moves 2 feet. Then the platform would move 2 feet, and the center of mass would have shifted 1 foot over. And that doesn't explain. Now, this relies on this relies on, as this disc is precessing over here, its mass has to be reduced or nothing is accomplished. Now its mass isn't going to zero, and I'll explain that later on, but it has, as it's precessing, it has reduced mass. And if that were to be demonstrated, if you had a big 100-pound flywheel here with I'll say a 5-foot radius, and it's precessing naturally due to gravity, if you put your hand in front of it, it'll stop it. It has very little force, except for it's not a perfect flywheel, but the rod, the axle, which is probably not spinning, has some angular momentum to it, and so, but it'll be easy to stop it. But if you had a 100-pound or 40-pound flywheel not spinning and rotating, being driven, just coasting, you put your hand in it, it's going to bump you out of the way and just keep on going until you slow it down. That shows that the non-spinning rotor has a lot more momentum, a lot more inertia than a spinning rotor. And later on, I'll show you that is a rotor in the form of a solid disc. A different type could be like a bicycle wheel with thin spokes and all the mass in the outer rim. In fact, if all the mass were in the outer rim and the spokes weighed zero, then theoretically, when it's precessing, it could lose all of its inertia. But I've developed some equations that show that if it were all in the outer rim, it would lose all of its mass. If you get a solid disc, it can lose at the most 50% of its mass, which is a lot, plenty enough to work with. Here's 2 of them. Okay. Now, yeah, that was 2 of them. It turns out that while it's precessing, it's not providing thrust. So if you want to have continuous thrust, have a second one, the one that's thrusting while the other is precessing, and then this one is thrusting while this one's precessing, and so forth. That's a very, very oversimplified example. It's sort of like a 2-cylinder engine. This was the 2-cylinder version. And now I didn't have time to finish this drawing, but this here is the same basic principle. Here, the flywheel is rotating like this, and so it is scooted or drugged from here, and it goes up, and it's no longer being supported. It's no longer being supported, and then it precesses back. Let's see. It precesses back to here, and then this flywheel is spinning like this, and it scoots from here, and when it comes up, it's airborne, and so it's not supported. Now it precesses back over to here, and it meets an obstacle, so it stops precessing. It comes down and it scoots back over to here, and it lifts up and it precesses. So it precesses, scoots, precesses, scoots. When it precesses, there's no motion of the frame. And when it scoots back, like I'll give another example. If that were 100 pounds and all this frame weighed 1 pound, when this V-groove collar is scooting it, when it's moving this 100-pound mass back here, the carriage is going to move forward this way. Then it's going to precess, and the carriage will move back only slightly, and then it'll, when it scoots it back, so it's a cycle. Now, a problem that you have to deal with is when this scoots it back and the axle is going kind of fast. This is an extremely simplified version. Now, I've had this version running, since last September. When it scoots it back, it picks up speed in a simplified version where you don't have controls over the speed, and you might say it bangs into here, and it's an impact that moves the system backward, which causes you to lose some of what you've gained. Now, this track is supposed to be circular. In other words, we'll call this 0 degrees. We can call it 0 degrees over here and 180 degrees. And this track, if you make it precess all this way and then get scooted back all the way to the 0 point over here, then the impact will be lateral. Here the impact is backward, and that sets you back a little bit or a lot. But if you make a 180 degree one, then that impact will be lateral and it'll jerk the thing sideways. But if you have two of them opposing each other, then their lateral impact will cancel each other, and the system will move forward and stop. The bad lateral reactions will be canceling each other. Then it'll move forward, and now obviously when it stops, you ought to have another pair of them so that they would be providing motion while the first pair is stopped. So one pair of them is precessing while the second pair is scooting. Then this one scoots while this one precesses, and if you engineer it right, you'll have uniform motion. But this is like a different configuration, and there's when it bangs into there's the problem that you got to deal with. The first one, which went all the way around in a circle, does not have that problem at all. And it's a little harder to implement because you got to build a support ring and a V-groove track. Now, I marvel at some of the devices that people have built. I don't have a fancy machine shop or anything to work with, and so some of my designs are on paper, but I know that there's people here who could build something like that for me in a month, and I might do that. I haven't had that done yet. This is different from the other one only in that the retrace track is straight, because in the other one, as it's retracing like this, there's lateral forces on it, and the actual path would be kind of like this, and you can design it so that the path is straight. And this one just intended to have a straight. Can you back that one? Back it up a couple. Okay. No. Okay. Now. Okay. Now this here is based on a configuration that Dr. Harold Aspton published in a magazine like 20 years ago, and it's interesting. This is supposed to be a torquing motor, and these are supposed to be gears. This is a central column, And these are two, there's a rotor with its motor, and this is a reset arm with the reset solenoid, and there's a pair of them, because if you have only on one side, it's totally unbalanced. And this here is the vehicle. It could include a cockpit, for example, for people or instrumentation. This is, I'll call it a shock absorber. It's got springs and hydraulic shock absorbers in it to smooth out any motion. And here, if you torque this central shaft like this, they're going to move up. And of course, if you start down here at, say, minus 30 degrees and move up to plus 30 degrees, you get the greatest effect. And that's a good way to work with, because that's an equilateral triangle. In fact, if the lever arm were, I'll say, 1 foot, then this motion is 1 foot for every cycle. And when it reaches the top point, it could be 30 degrees, it could be 60 degrees, then it's reset. You stop the torquing force and you reset it, then you start the torquing force up. So it's basically like a square wave driving the forcing torque motor. And the opposite side of the square wave drives the reset function. And now, when it's torquing, this moves up. And if it had zero inertia, which as I've shown, it could have at the most, it could lose at the most 50% of its inertia, there would be, as it moves up, there would be just a slight downward reaction. But when you stop back it up, when you stop the forcing torque, it stops moving up, and when you reset it, you're moving a heavy weight down, and that raised the chassis up significantly, and then you repeat the cycle. So while it's precessing up, it moves down a little bit, but then when you reset, it moves up a lot, then down a little bit, then up a lot, and so it actually comes to a dead stop and backs up a little bit in this configuration. And so that this column isn't totally out of balance, you have to have an equal and opposite one here. And this just shows, with the one-sided system, at configuration A, the reference point is 0, and at B you apply a torquing to it and it starts to climb up. You continue the forcing torque and it climbs up higher, like maybe to 60 degrees or 45. And suddenly you stop the forcing torque. This curl shows a forcing torque. You stop the forcing torque and you reset it. When you reset it, the chassis moves up. And then you repeat the cycle. Every time you reset it, the chassis moves up a little bit. And you keep that up. And this here, again, using good old SolidWorks, it shows, well, first off, if you had just one of those, it's going to move and stop, move and stop, move and stop. So you need another set that's that will be moving while this one stopped, and that'll give you more uniform motion. And if you rectified just the output from one, you can see that you've got a varying velocity and then no velocity. Actually, you might have a slightly negative velocity. And if you had, right now, I've forgotten the reason, but this is the minimum operational platform that provides you a good uniform velocity. It's a little hard. Now, if you rectify the motion from that, it's not constant, but it has at most a plus or minus 6.7% ripple. That's easy to filter out in engineering terms. In engineering, you use a little bit of inductance and maybe a little bit of capacitance. And here that would be used by springs and hydraulic shock absorbers. And so you could get uniform motion if you built a vehicle that would house people. And just for that reset track, you can have a V-groove, you could have teeth, or just a friction surface. And a friction surface is what I've used in all of my devices. And instead of having gravity pull down on it, you could have a magnetic ring where the top of it is the North Pole and the bottom is South Pole, and it would pull down on the rotor, or it wouldn't have to pull down on the rotor. There could be an object, an iron object at one point, and this would substitute for gravitational field, which would make it work in outer space where you don't need a gravitational field. And here's a different thing which I'm not going to talk about, but it used a magnetic torquing device. Here, this is a special configuration. I call it the rolling pin rotor. This is the motor. Instead of having a big rotor like this, if you cut the diameter down a little bit and increase the length of the width of the rotor, and you cut the diameter down more and increase the width of the rotor more, and you keep it up until the width of the rotor is no greater than the width of the axle, and now it's real long. It turns out that with that configuration, and if you have this quadruple arrangement of it for uniform motion, you can develop the highest velocity with the rolling pin rotor, but that will not develop the maximum horsepower. The horsepower is a function of the angular momentum of the flywheel, and this does not have the maximum angular momentum. It will, however, give you maximum velocity. And again, this is a if you use that non-practical thing, it shows moving an object without any force involved. And here, this is just, I'm working on the equations for this right now. If you, instead of having a constant forcing torque, you apply a linearly increasing forcing torque, you will get a velocity output that does accelerate, but that acceleration ends when you do a reset to it. And being that velocity was not perfectly straight without being filtered, it's got humps like that. You could shape the reset pulse so that the velocity output is constant for each subcomponent of it. This is in what I would call a preferred embodiment of whichever configuration. Now, someone a year ago mentioned, hey, how about a solid state device? That was a very good idea. And there are certain parts of it that you can build solid state. Assuming that you could do the whole thing solid state, here's a forcing torque and a solid state unit and the velocity output. And this is the equation for the velocity that you can achieve. And you can see that if you take the length of the axle over its radius times 2 over the frequency, the spinning frequency, in other words, it's the square of the length over the radius. That's what gives you the maximum velocity. This was nothing. Now here, this just shows how I calculate this ripple factor. And now this is significant. Here's equations for the reduced angular momentum and centrifugal force. Now, the equation for the moment of inertia of a hollow cylinder is m times the first radius squared plus the outer radius squared, or maybe the inner radius squared, and the outer radius squared, and so forth. Now, you'll see that if for a solid rotor the inner radius is 0, it's a solid rotor. And that equation goes, the angular momentum is divided by half. If you had the outer radius and the inner radius equal to the outer radius, which would be a hollow thing with a very thin, all the mass in the very thin rim, the angular momentum goes to 0. And of course you cannot achieve that. You have to have some spokes and you have to have some thickness to the rim. But it shows that if you go for a disk configuration, I believe that these equations give you the correct reduction in centrifugal force and angular momentum. Here, John helped me conduct these tests. I was going to say, like for a torus or a hoop type thing, the equations are slightly different. But that's irrelevant right now. Here, it analyzes the forces on the axle or the lever arm. And this is where the weight of the rotor acts at the end of the axle. And M is a moment applied by the tendency to want to precess upward. And this analyzes the shear on the rotor and the bending moment on the rotor. And here's a configuration. This shows the forcing torque. And if you made an equivalent model, which engineers are famous for doing, here's a pivot point just sitting on it. You'd think it'd slide off. You'd think the rotor would fall off, but it doesn't. It precesses. This is an exact equivalent model where as the rotor moves up, it has to be able to move in or out because its radius changes. And it can move up or down because it's in a cylinder, and it can pivot about that point, and it's got a firm grip on the end of the lever arm, and its weight is here. That's free to move along that, and this applies the bending moment, which is equal to the weight times the length of the, engineers who design a system would want to use these type of equations to make sure they don't make the axle heavier than they need to. And it's interesting in one of those first configurations where the rotor's scooting back, the weight of the rotor is not on the axle, it's on the frame. And when it's precessing, the weight, it's at the pivot point, and the axle doesn't have much stress on it. It's a very unique situation, which means you could have a very thin rotor shaft supporting a very heavy rotor. This is the first device that I built, and I was going to bring this along, but it was such a crude device that I want to show something a lot better. But here, this is just the plastic from a gallon jug, and it scoots back here, and it comes up here and gets no longer supported, so it precesses back to this point. I put a bearing out there so that it wouldn't, when it hits that point, so it wouldn't slow the flywheel down unnecessarily. And so it goes like that, and when it's scooting back, the frame moves forward, and then when it bumps into this, it cancels some of the motion. And now this here,
in the Fiala's garage. My name is Harvey Fiala, and here's a device that provides inertial propulsion and also converts linear motion to rotary motion to linear motion. It fell off the roller overbound, so it's going to quit.
wow.
28th,
Okay.
2000.
I'm going to stop it there. Actually, you can see that isn't motorized. I had to spin it each time, and if you jerk on it, you can upset the whole thing. So it's very tricky to do. And you can see that it moved forward like an inch every time or something like that. And if you practice, I had to do 15 oscillations before it damped out the energy of the flywheel and it wouldn't precess. And if you're unlucky, it won't, if you do something wrong and there's no control on the speed, but it's a crude device, and I want to show something better. Now you can see I had rollers on it instead of wheels, and once it rolled forward off the wheels, off the rollers, it fell down and couldn't move anymore. And I'll play that.
6 in the laboratory in the Fiala's garage. My name is Harvey Fiala, and here's a device that provides inertial propulsion and also converts linear motion to rotary motion to linear motion. It fell off the roller overbound, so it's going to quit.
Wow.
28.
Okay. My son James videoed this for me last year, and I was going to bring that along, but it's too much of a contraption. Here's one of the test devices, and there's yours truly displaying it. Okay, I'm gonna mention here. This is just something for you to think about. It's a thought exercise. I started a gyroscope at about 75 degrees or something, and it raises up. In other words, the center of mass is at a certain point there, and its center mass raises, means work is being done, and obviously the work is coming from the kinetic energy of the rotor. And I'm asking some of you guys, can you figure out how the energy mechanism transfers to raise itself up? See, it's
put it
slowly
on at
raising
about
up.
70 to 75 degrees. Now it did a self-climbing act. Now it's losing precession. Is there centrifugal force or angular momentum right now?
Okay, I'm challenging anyone, not now but later on. If you think you can explain that, I have the answer. But I mean, it shows that you understand significantly about. Is this the last? Okay, there's my home phone and my email. That email address is wrong. It should read, instead of Comcast, it should ca.rr.com. And CA stands for California, and RR stands for Roadrunner.com. And I think that's it. And now I'm going to demonstrate my famous hardware. This is the good news here. I have a son-in-law, Steven Sanchez. He's worked for 30 years for what's now Boeing, and he machined a few precision parts. This is a rolling pin rotor. This one's of steel. He made one of aluminum for me and one of titanium. I wanted to experiment with it. Only I didn't do, and he made a little pedestal here and a little gimbal system, and inside of that is a small motor, 1/4-inch diameter, 3-volt motor, and it has teeny-weeny holes in the ends of the axle, and this is the only one that had a deep enough hole in it, and it fits pretty snugly, good enough. And I put a 1.5-volt battery on here, and it didn't have enough power. In other words, I didn't have enough time to do the homework to realize that I got to have a lighter rotor for that motor. So I tried 3 volts on it, and it started moving, but it wasn't good enough. I tried a 9-volt battery on it, and within 5 seconds it burnt the motor out. I put a new one in, and I was going to be more careful this time. So within 3 or 4 seconds, the second motor burned out. This time I was going to be far more careful. This one time it burned out open-circuited instead of short-circuited. And this was done the day before our plane took off. And so I got 30 minutes of sleep that. But anyhow, this was, I was planning to demonstrate this, and to demonstrate this would have sat inside of, you know, I'll say a quart, a 1 quart container, or a 2 quart container with that cutout in it for it to scoot back and precess, scoot back and precess, scoot back and precess, scoot back, and it would have done that, except ran out of time, and that's my famous part there. If anyone has any questions, we have 10 seconds left for questions.
We've got time for about 1 or 2 questions, and then we're going to ask Harvey to go stand over there while Stephen Greer gets ready. We'll take 2 real quick.
So, which embodiment qualifies as the one moving part propulsion?
That's right. That at first it sounds unbelievable, but here the motor and the rotor is only and really the gimbal assembly. The gimbal assembly can be simpler than this in this embodiment, but it's got only one moving part. In other words, there's not a batch of gears and pulleys and all this contraption. It's so simple, but it does a limited amount of good for you. But this can have applications in, see, when this moves, if you design something, like I've said, if you spend $1 billion in development of this instead of automobiles, you could design a Lamborghini that'll do 0 to 100 miles an hour in 1 second. And it'll stop in 1 second also, and if you look at UFOs, they say, hey, there's UFOs, and they turn a square corner or they accelerate suddenly. Well, all the attributes that they've attributed to UFOs can be done by simple MMT, motion by mass displacement or mass transfer. And it doesn't even take sustained acceleration. Now, I'm working on sustained acceleration. I've had a configuration that might do it. In fact, my mathematics says it should do it. I've submitted it I've asked 3 PhDs at MIT to analyze it for me, and they won't give me an answer. And I've had a retired emeritus professor from University of Idaho working on it for 9 months now. And at first he says he'll do it, analyze, send me the result in a week. 2 or 3 weeks went by and I didn't hear from him. I gave him a phone call or an email. And he says, well, it was harder than he thought. He'll get back to me shortly. A couple months went by.
Maybe they're trying to keep it for themselves.
Well, no. In other words, it's either works and he won't tell me, but it takes what you call, it's a dynamic analysis of some mechanical configurations which involve the force of gravity. If it works, many people would say it violates the Newton's law, which says if something moves this way, there's got to be reaction this way. And I say it doesn't. The reaction, the angular momentum of the device Earth system is preserved. It's just, you won't see the conservation of angular momentum in your unit, but it's in the Earth that and it takes what you call Lagrangian formalism to solve that set of dynamic equations for that. And I made a simple assumption, which I didn't tell him. I solved it, but I made a simple assumption, but I wanted him to solve it all the way dynamically so I can analyze it any part of the cycle.
Ladies and gentlemen, I'd like to close with a personal note. Working on some of this with him has been very exciting, and there's been the places where we've looked at the scale, and the scale's lost weight, and these elusive little bunny rabbits that seem to appear in the little green people from Minnesota, the gremlins. And we even had one that was about 66 or 68% of the weight just disappeared, and depending on which way you polarized it, and things that locomoted right and left without or with reaction. But I'm very proud of the work that's been done, and I think right now the first definitive work in inertial propulsion has been done. And I know that everything I do, I couldn't survive 1 minute out working in the shop without somebody else taking care of the home fires. And behind, they say any man can make colonel, but it takes a good wife to make a general. And I know that this man also has a good wife, and that just everything that he puts in, she puts in also. And this year is their golden anniversary. Ladies and gentlemen, Harvey Fiala and Bonnie Fiala. We'll see you back in 10 minutes. Thank you.
I'd like to make one closing statement here. This is the year of our 50th wedding anniversary, and we have 5 sons and 5 daughters, and 4 son-in-laws and 4 daughter-in-laws, and 12 grandsons. We lost one, by the way, which would have been 13th, and we have 12 granddaughters, and we have one great grandson now. And unbeknownst to me, my wife and my daughter scheduled us to away from home for a whole week right before presenting this, and that wiped out my schedule, sort of.